the high mountain wind with like usual surround wind.
It's got low top boots.
Alright. Hi, I'm going to be talking to you about the hydrodynamics aspects of the underwater deck. First, I will remind you of the main parameters of this part of the mission. I'm going to move on to what I've done so far, and I'm going to finish off with the future steps I plan to take. So the underwater phase, there's 2 legs of 1200 miles each. We expect to cover it in around 3 hours each leg, which gives a speed of 4 knots. The Reynolds number sits somewhere around the 8-10 million, and we're going to be traveling at 40 meters depth, and we're going to be propelled by a pump jet engine with electrical supply. So my aim is to optimize and analyze the performance of an aircraft underwater, since we're going for a submergible aircraft instead of a flying submarine. So the first step was to sort of shape the fuselage, the lateral view of the fuselage. So I had to choose a length to beam ratio, which is sort of an lateral aspect ratio of the fuselage. Since it's a streamlined body, we want to minimize the drag, and the 2 main components of this are the pressure drag and the skin friction drag. There's sort of a flat minimum around the region between 5 and 8, and since I got these values from the system C, there's a length to beam ratio of about 3.2 there, and still missing the total and all this. So I selected 5 as a startup point. So the ideal base shape, it's ellipsoidal at the bow and paraboloidal at the stern, which is sort of saying that we're going for an airfoil shape. But the main difference is that we're going for a parallel mid-body section. This has very little drag penalty, according to Professor Jover down there, and it improves the draft and the building cost. It reduces the building costs. So for the airfoil selection, I wanted an airfoil that was symmetrical, so we wouldn't generate any lift during the underwater cruise. The thickness, I wanted, it had to be over 20%, since we're going for a length to beam ratio of about 5. And I also wanted a very low, to minimize the drag coefficient at 0 angle of attack, which is what we're thinking we're going to be, the instruments we're going to be going during the underwater cruise. So I selected the Jocos K0021JF, which is an airfoil with 21% maximum thickness. The CD is under 0.01 at 0 angle of attack, and we also have the advantage that the CM is balanced in a region around like plus minus 8 degrees around the 0 angle of attack. So if we go nose up or nose down, the hull will help in balancing this back to 0 angle of attack. Other sources of drag include the roughness, which I'm going to be talking in more depth later. Fouling, which increases the skin friction coefficient by about 1/8 for each day out. This is not going to be a problem for the whole of the hull, but it's going to be a problem for the lower surface, which is going to be sitting in the water during the 3-day boat journey. So that will sort of increase the skin friction coefficient by about half, and it will actually change the hydrodynamics of the hull when in between the outbound and the inbound leg. Control surfaces and hinges are also important and contribute to the drag a lot, since they tend to favor separation and also transition. There's holes, float openings, and finally inertial forces, which are modeled using Morrison equation. Unless we are operating at sea state 5 or similar conditions, it shouldn't be a problem. But since that's the extreme conditions, we should be designing for, according to the brief, something that we'll need to look at in the future. So the factors that contribute to roughness are all of those. It basically increases the skin friction drag massively for submarine flow. And so I started looking at possibilities to get around this. And for example, shark skin, which has been around for a few years, and it's basically used for drag reduction in turbulent flows. And as I will show later, turbulent flows will be a big chunk of the kind of flow we will have around the body. So boundary layers. Ideally, we would want natural laminar flow all along the fuselage, but that's not possible. Under ideal conditions, we'll have Reynolds numbers of around 10 million. For our G, which is Reynolds number of about 10 million. The point of instability coincides with the point of minimum pressure, and the point of transition sits straight up. And in reality, transition happens even earlier due to roughness and tripping devices, such as holes and float openings and all of this. One more thing, we are also concerned about noise, not only drag, because we are traveling underwater and we want to avoid detection. Since these two come usually hand in hand, but usually turbulence is less noisy than transition. So ideally we want to minimize the transition regions we have around the body. And we definitely want to avoid separations since it's very draggy and very, very noisy. For the nose design, we want a circular cross-section because it's the most efficient structurally, gives the lowest stress and lowest water area for a given volume. We need laminar flow at the sonar position. I've already spoke to the systems guys about this because we want accurate data. So we want the sonar as forward as possible, and we need to have laminar flow in that region. Finally, if asymmetric, which it will be because we'll need to design it to land and take off on the water. The asymmetry should start as aft as possible. Then the aft body design is basically the same principles. You want to minimize the pressure difference at every cross section, and a big difference with respect to the nose design is that we're going to have the propeller, the pump jet engine, sitting somewhere 3/4 of the into the body. So that's going to perturb the flow a lot around the rear part of the body, and that we need to take that into account as well. Finally, one common issue with submarines is cavitation, which is basically a change of state of water if the pressure drop in the section side is large enough. This increases the drag a lot and also induces a loss in lift. Since we're going to be traveling at about 5 knots, this shouldn't be a problem, as you can see on the graph. But there's another phenomenon which is called ventilation, which is sort of similar, but it also leads to a great increase in drag and loss of lift. But instead of vaporizing the water, it happens near the free surface, where it sucks the water from the free surface into the suction peak is large enough, and it creates the same bubble. That's something that will probably happen for our case when we're diving into the water and coming out to the surface. In the first case, it's advantageous because we can actually lose some lift there and sink faster, but it's going to be a problem when we come out in the water, so we need to bear that in mind. And finally, the next steps will be to end up the nose and aft body preliminary design, work together with Roshan on the optimizing the whole design. I'm going to focus my research on boundary layers, so I've got the Schlichting reference for behavior and drag estimation. I've got the Kashanov, which is review on methods for to predict transition, which is going to be quite important because I want to know which regions are going to be turbulent and which regions are going to be laminar around the body. And ideally, we would like to automate these calculations, coding them up, so I can give back data quickly when they come to me with a new design. Well, and the last point is just if I have time, there's this technology that's been out there recently, boundary layer and vortex control mechanisms to delay transition and counteract the undesirable effects of vortices and cross flows. And that's it. So, questions?
If you can go back to the airfoil you selected, where did you get the data from?
Airfoil tools.
And what type of data is this? Do you know the source that they use to actually?
Yeah, Java. Well, I'm not quite sure.
Something to pay attention to when you find things. you were talking about fouling
Yep.
as well. Does this suggest that from the first day that it goes into the water, barnacles are going to catch on right away and we're going to get a 1/8?
According to the author of this paper, which is the same, I've been taking most of the what I've been following for the design. It says it increases that by that much.
You say it increases by 12%. Is that as in 1/8?
Yeah.
How are you intending to optimize your hull design?
Well, I'm gonna give Roshan my design, and then he's gonna design for the lower surface for takeoff and landing, and then based on that and the wings, the other numbers are gonna be.
So, so the Joukowsky is your starting point. Is that the?
Yeah, that's my starting point.
But you're going to modify that.
Yeah.
You're going to what? Keep the nose geometry and make it thinner. Is that the idea?
The idea is to sort of get a thorough mid-body section from the beginning, and then for the nose design I was talking about here is more. It has more to do with the sort of front view of the. So we're gonna have this sort of similar to airfoil shape from the lateral point of view, but then we want to design the nose. So
Right. Okay. Because that's clearly a 2D airfoil. So how does that translate to a 3D?
Well, it's quite thorough this reference on nose design. So ideally, you should be able to do something.
Finally,
Yeah.
Are you sure that transition is the noisiest process? What's
Not noises than separation,
Okay.
but noises and turbulence.
Okay. What reference is that?
Same.
Is that a certain? Is there a graph or a certain?
Well, I can look it
Conditions
up.
when that's the
I can
case.
look it up now.
Well, it seems a bit surprising. I can imagine transition might have particular tones associated with it. Like there might be a lot of
Well, yeah,
acoustic energy at certain frequencies. I would imagine that your turbulent flow is going to give you a more broadband noise.
Might be referring to that is going to be easier to detect by
Okay.
an enemy force instead of being more noisy.
Oh, I'd be really interested to hear more about that.
Sorry. Sorry. Any more questions?